All right, so hello everyone. So today let's talk about the sloppy code structure, and I will introduce the code details for sloppy. And there are two set of contracts we need to learn. First is called sloppy core, and the other is the router of the sloppy. So first, let's introduce the sloppy core. So the meaning of the core is the pair uh, the the pair of two tokens uh, and why it is called core, because there uh, the logic is in sloppy core is the most important, and all of uh, the two tokens will be stored in the sloppy pair. So first, let's talk about the interfaces, and the first is called IERC20, which means so the two tokens are must follow ERC20 token standard, and the two tokens can be stored in the floppy pair. And each token follows the interface declared here. First, there are two events called approval and transfer. Approval is just approve spender to spend some fixed amount of value from owner's balance, and transfer is just transfer from source to destination as the amount of the value. So there are two events, and the remaining functions are already introduced in the last sessions. There are very simple functions. So the first three is just the these six functions are read only. It will return the name of the token, symbol of the token, the total decimals, and the current total supply, and check the on some users address balance for this token, and also check the spenders the amount of the token for spender to spend owner's balance. And we can also the three functions are for do approval and transfer. And approve is just approve the spender to spend the value from the message dot sender, and transfer is just transfer from message dot sender to pool address. And transfer from, you can transfer you can change the sender. So that's the three functions, and we will use some of these to be used in the sloppy pair. The second is called sloppy call. I will introduce later. This is for the for some random users smart contract. They want to do some following calls after swap or after adding or removing liquidity. So in the so because the interface has the function names as the small p call, and the user smart contracts must have the same function name and the same arguments, same function prototype. If you want to call it, I will introduce it later in small p pair. And the next one is called iSwap ERC20. So this one is for so the swappy pair has some shares. We call it liquidity shares. So as long as the users add liquidity in the swappy pair, you will get the uh, ERC20 token. And there are, so this is advanced version of a ERC20, which will follow which is the liquidity share we want to give to the liquidity provider. So it's the same functions. There are more functions to identify the unique ID of the current swappy pair shares. So these new functions will be used in the swappy pair contract we will introduce later. Next one is the one called iSwappy Factory. So this is the interface of the Swappy factory, the facility. It just gets some useful functions, and some other projects can take use of the interface instead of pick up the whole contracts to call some functions. So these functions are be used by other easy to be used by other projects. I will talk about the Sloppy Factory usage later. And next one is the Sloppy pair interface. I called iSwappy pair. It's also the interface of the Sloppy pair. It just lists all of the not all of them, just all of the useful function prototype and some useful events listed here. And I will talk about later. The next folder is called libraries. So the libraries stores all of the mathematics logic calculations. So for example, first we need to declare it as a library, and this library called math. So you just determine, some like minimum function and the square root function. There's no square root operator in EVM or in Solidity, so it's easy to just implement a square root using the divide and divide and plus and some while loop to do some loop to estimate the results of the square root. So if you're interested, you can just read through it and see what happens here. And here I just skip it. And next is called safe math. there are so many, so many dangerous operations in Solidity. Uh, uh, so the most typical one is called overflow and underflow, which means, for example, you add something, you add x plus one, y, it will go over to the 256 minus one. So the number will be, overflow it to be, it will change to some value less than some input. So some attackers will take use of these overflow operations to to do some attack and steal some money. So here we use a require statement to check it is overflow or is underflow. Underflow is, so when do the subtraction, it get a negative number, so it's also doesn't allow to do it. So, and is as well as the multiplication. So x times y must not be greater than 256 minus 1. So we also need to have a check. So that's for called safe math. Next is for uh, some calculations for the 112 bit with unsigned integer number. So if you, like, for example, if you want to change encode 112 bit with to 4 bit with number, you will invoke encode, and also you can do the divide 112 times 112 number by you int 112, and you will get 224. So you will these three mathematics calculations will be directly used in the sloppy pair. So that's called so that's for the mathematics libraries. And you can so this one is called migrations. You will migrate the all of the old version of the contract to a new contract. So we will use the migration.sol, but I think it's not needed in our project, so we can skip it. The next is the sloppy the actual sloppy ERC20, which will be used as sloppy pair shares. So the first line, so first import the SafeMice, as I mentioned before, and the interface as sloppy ERC20. And here is just sloppy ERC20 inherited from the interface, just inherited all of the function prototype, and you can implement the details here, which is same as the C++ class inheritance is the same. And these statements, which means all of the uint integer as as known as uint 256 integer will be all of will use safe math. So you don't need you don't need to do something like, so if we don't have this code, we may do something like save math. If we want to add something, we need to do a and b and c times something like that. But if we have this sentence, we can do a dot add b c equals to, yeah. So you don't need retype safe math just for for easy to use, and also it's pretty clean to title it in the at the beginning of the contract. And here we will define some constant. So there are constant values, and there are strings and integer 8-bit with integer, and they are all public, which means all of the other contracts can directly raise the name, and the also the users can directly read the name by invoking the name function, symbol function, decimals functions as mentioned in the SWP ERC20 interface. So you declare it as, so this share, SWP share, is called SWP LPS, and the symbol is called PPI-LP, and the decimal is 18. And here we declare a total supply, right? So we need some value to record all of the total amount of the shares. And we did a mapping variable called balance of. So, and we can, so this is also mentioned in the interface, but the interface, this is a function, but it doesn't matter between this function prototype and this storage variable, because whenever we invoke or call balance of function to raise the balance, we do the same thing. So if it's a mapping variable, if we raise this balance of, we need raise same as the function. So we still use a balance of user to get the user balance. So it's the same thing. So here it can be use of a mapping variable here to override the interface balance of function prototype. It's the same thing for allowance. So here is a 2D mapping. So there are two index for address, and the value is the integer. Let's go back to see the allowance function prototype. So you see there are two arguments, and this is the two indexes in that 2D mapping array. And the result is a U integer, which is the value of the 2D mapping. So this mapping variable is, when we read it, is the same as to read Lawrence functions. So we may read it like you address A, and the second argument is address B, and that's it. So it doesn't matter. So that's for balance of and Lawrence. And domain separator and permit type hash. So domain separator, a separator is, is just identify the unique number of the sloppy share. So you will define it. And permit type hash is the hash. So this comment is just to the hash of this function prototype permit, and the argument is owner spender value nonce deadline, and I will introduce later to how to use the type hash to do some permit. And nonces is the nonce of the user, which will be used in the permit function as well. We will talk about later. And the same as the interface events, we declare approval and transfer event. And also you can leave it blank because it's already declared in the interface. And you can leave it, and the events will be will be inherited. And if you declare here in contract, it will override the old event prototype. So it's the same. The next is for the constructor. So first we need read the chain ID. Chain ID, yes. So here is assembly code. So this chain ID will be rated. So this chain ID is the built-in variable in Conflux space. So in assembly block, you can directly read it and store it into the chain ID, and we use this operator to read and store. And then we do some hash char to 56, do some hash, and encodes all of the the features, the feature code, and after encoded, do hash again to form into 32 bytes. So domain operator will be always as 32 bytes array. So it can, so the sloppy pair will be this so this constructor will be used in the next level, next child a sloppy pair, because sloppy pair is inherited from this contract. So when we constructor, when we create the sloppy pair, it will invoke sloppy ERC20 constructor first, and then invoke the constructor in sloppy pair. So in this contract, it will in constructor, it will confirm the domain separator, and yes, and that's it. And as ERC20, need some, mint and burn function. So here is the mint internal function, which means it can't be used in external contract, and also you cannot read by others, by other EOA or contract address. So for mint, we need set the argument is the destination address and the value to be mint. First, we need increase the total supply. So as we mentioned before, we use a safe minus, so we can add the value. We can directly write .add and the argument is value, and total supply will be plus to value to be reassigned to itself, and also updates the balance of array we mentioned before. So index by the destination address and increase the amount of the value, and then we emit the transfer events. We emit transfer events because it's mint. So in the on-chain ecosystem, if whenever we say it is mint, we will emit the transfer events from zero address, which means it's from from void to some to the destination address. So the from is address 0, means 0 address. It's the same, similar as mint. The burn has the target address and the amount of the value. We need invoke the sub to decrease the value. Total supply did the same. And so in this case, for burn, we will transfer from the target address to 0 address with some amount of value. Next is for approve. So if we approve some some spanner to span value, we need increase the we need set the allowance. So first is owner, second is spender, and directly set the value. And also we will emit the approval event. If we do transfer, so we need updates the from address and to address balance of variable, do subscription and addition, and then emit the transfer event. So these four are internal functions, so no one can access to it. But so for the functions in the contract, it can access to the internal functions. So here we define approval, and this is external functions, which means the user can directly to approve to call the function. So here we invoke proof. So inside we will proof is, of course, we will the from is the most message.sender, which is the sender of the transaction to invoke the function. And the destination address is the spender, and the amount is the value. And transfer did the same thing. The from address is the message.sender. And transfer from. So transfer from is a tricky one, which is will take use of the approve event. and it's also generally the transfer from followed by we will follow approval function, which means the approval must be happen first, and then we can do transfer from. So whenever we do a transfer from, we need delegate delegate, or the message sender must be the spender of the address from. So here you check it has something or not. So if there is a Lawrence in the array, you will do the subscription and transfer to the destination address. So why here we don't need care about if the allowance is smaller than the value, what happens, because we use you use a safe math library. So the safe math library will through the arrow. So we can do a quick review. So in safe math, we do a subscription. It will pass through a require statement. So as long as the x minus y is less than x, it will through the arrow and revert the function. So which means it will throw error if the Lawrence is smaller than the value. So we don't need to care about in this contract level. You can directly invoke .sub function and without any check, underflow check. So that's for transfer from. And last one is the permit. So the permit is which means these three variables are present to the signature components. So whenever we send a transaction, we need sign the data and also send the signature. So the signature is combined with this variable. So in this function, it will span some owner will allow a spender span some approve owner for the owner will approve the spender to span some value, which is corresponding to the last statement. But this function is not invoked by the owner. It will be this function can be invoked by anyone, but the signature is the most important one. It will so in this block we'll check the signature corresponding to the to the to the approval operations. So first we will check the deadline. So the owner will set some deadline to do these operations. If it's over the current if it's less than the current timestamp, which means it's expired, it will throw error. And here it will encode the message. So this signature will sign the message in off chain. So in on chain we need encode inside the inside the contract. So there, encodes the domain separator as we mentioned before, because it's unique ID, and the permit type hash, and owner spender value, and nonces. So the nonces will be increased one by one, just in case you can permit double times. So we will increase the nonce every time we do run the permit, as well as the deadline. So this message will encode all of the necessary informations, the information of the swappy pair, and all of the data will be used in this permit function. So here is check the regular check for the signature is valid or not. And then this function is pretty useful. It will recover, so which means it will check this signature, this message hash is actually used by the signature from the owner. So it will recover. So after it checks, it will return the address, and the address must be the owner address. So in this way, it will, which means the owner provides is the signature of these functions informations, and the on-chain contract, and this block will refactor the message and use the provided signature to recover to the public address for the owner, and the owner address must be the same as the recover address, and of course the owner must not be 0, because it doesn't make sense. And after check everything is fine, we will approve the owner will approve the spender to spend fixed amount of value of the shares. So that's for permits. It's pretty interesting function.